Hello and welcome to They're Just Robots, podcast on robotic control. Brought to you by Enforced Social Isolation and Harun Sheikh.
Thought you had plenty of friends, more than you could ever really want. But really, sometimes they're not what you need. They can't do it all, cause they're only human. True kind of pal would drop all that she's doing. You need a true friend, and we've got lots. They're just robots.
And so it starts. This is They're Just Robots. And it's a very Star Wars podcast in the sense that we start with episode 7. So the first 6 episodes, which were delivered live in the EE413 course, will probably get recorded later once I have time. So that will be the prequels. But for the time being, we start with episode 7, motion control. And probably this episode is gonna get a revamp, just like Star Wars films got a revamp whenever George Lucas felt like it. So all of this ad hoc recording, bad sound, and all the ums and ahs are gonna get removed. And maybe I'll do something about that. Wild music, which is actually Learning Music's robotic anthem. Really cool song. Now, you can't really put a formula, an equation, or a graph in a podcast. In that regard, the They're Just Robots podcast is going to tell you the story of robotic control and the maths, the graphs, the charts, the equations, the schematics. That's going to be delivered in a different way in EE413. The podcast is here to give you an overview, to give you a rationale, to give you a cool story to share with people if they're inclined to talk about control at some point in their lives. So that's pretty much it when it comes to the housekeeping rules of They're Just Robots. And that being said, we can start with the topic of episode 7, and it's motion control. We were ready for motion control already when we talked about the story of trajectory planning, because we said already there that trajectory planning is going to deliver reference inputs for the servo motors, for the manipulator itself, its actuators, how to move in the space to deliver that particular control task from going from point A to point B. When we talked about actuators in robotic manipulators, we left the whole controller part there as sort of a question mark. So we knew where the controller fits inside the loops that take care of the motor control, but we didn't say how exactly we designed them to perform motion control, because there's a whole separate episode for that, and that episode's today. So let's see, how does motion control really work, and how many different ways are there to perform motion control? First of all, just like in the story of trajectory planning, you can do it in the joint space, you can do it in the operation space. Joint space will always feel natural to the robot itself, while the operation space will always feel natural to everyone else, because robot exists in the operational space, but of course it performs its motion in the joint space. The motors themselves see, quote unquote, the joint space. In today's episode, we're going to focus mainly on the joint space. For the operation space, we have the next episode. Under the umbrella of motion control, you have proper motion control. So the one that makes sure that a trajectory planned is the trajectory delivered. But you also have interaction control that has to take care of the interactions of the manipulator with the environment. Interaction control is usually carried out in the operation space because that's how the environment is described, and that's where the robot is performing the motion. So bumping into things, that's again for the next episode. In today's episode, it's all smooth sailing. It's all just trying to deliver a motion of our robot that exists on its own in its universe. And while our robot is all alone in its universe, it's probably not just one actuator, just one joint. It probably has quite a few. And the question of how do you coordinate all these joints is the question of decentralized versus centralized control. In centralized control, all the joints are taken together. Everything is coordinated in detail. Everything is taken care of at the same time. There is a quote-unquote conscience of the wholeness of the robot and all the effects, all the couplings, all the interaction between the robotic joints. On the other hand, in the decentralized control case, robot is observed as a superposition of multiple joints operating independently. To do anything as a superposition, you assume linearity because, as you may remember from any course on systems you had, linear systems have the basic property of superposition. Do something to system A, do something to system B, add those up together. It's pretty much the same as doing something to A plus B from the very start. Now we're also pretty much convinced already from all the physics and all the systems courses we had that linearity is a useful abstraction, but not really achievable in the real world. But you may remember, again from the actuators part of this course, that transmission really helps with linearity. That transmission reduces non-linearity the motor would quote-unquote see on the load shaft. And as such, well, if your manipulator has rigid transmission, you're pretty good to assume that the whole linearity concept will hold and that some sort of decentralized control wouldn't be too bad. Another thing you can be sure of, though, is if your manipulator has rigid transmission, it probably has a lot of friction as well. So do take that into account as well when planning. So now you may wonder, if it's nonlinear inherently, and we assume it's linear, where does all the nonlinearity go? Where does it fit in the model itself? Where can we put it as here be nonlinearity we're not taking care of it directly. Now I again have to invoke your memory of the actuators part of this course. And do you remember that we had the whole disturbance input? So there was this load produced by whatever else is outside. So it's not motor torque that's delivered in the system, it's the outside world. Well, that's exactly where we are going to pack the nonlinearity, the interaction between different manipulators, joints, different actuators, all the coupling, all the gravitational effects, all the inertial effects. We're gonna say it's disturbance. And what do we do with disturbance? Well, we try to reject it. So we'll always try in decentralized control to compensate somehow for this disturbance, not just caused by the environment, the outside, the big universe, which we did assume at the beginning here that it's empty, that it's just our manipulator in it, but sure. It's also the other parts of the manipulator that cause disturbance to this particular servo we're observing. So we'll have loops, control loops in decentralized control for each and every motor separately. And for each and every motor separately, everything else, all the other motors, all the other parts of the manipulator will cause some effect, but we will consider that effect disturbance. That's giving us a wildcard. We don't have to model it. We just put it there, being aware it's there, and hoping that our controller is just good enough to take care of it. And now in the next part of today's talk, we're gonna see exactly how the controller does that and how well can it do such an important task of compensating for maybe a dozen other components. Spoilers. It's pretty much all about PI controllers.
That dog is man's best friend. That might very well be true. But every bone that a canine bears, but to do better, steadfast and truer. Fetch any stick, bring your papers, slippers, available in fur, and they don't need wax, they're just ROBOTS rollers.
That sounds pretty simple, right? We just need to plug in a PI controller into one of those loops that we saw in the actuators part of the course, and we should be all fine. I mean, we did say that we're going to examine every servo separately. So every servo gets its own loop. It's all your basic linear systems now. And just now, since we have the giveaway that it's a PI controller, what's exactly complicated there? And why a PI controller in the first place? Well, you want a strong P component, a big gain to compensate for the disturbance. So you want your important signal to overshadow the disturbance signal. So the proper torque should be bigger than whatever other torque is coming inside to disturb the control loop. And the I component, as we always say, integral component is important because integral component removes the steady state error. And in this universe of ours that contains just our manipulator, there's still this particular force that exists that keeps everything together, gravity. And with gravity in place, there will always be a gravitational effect on our manipulator, and there will always be just that next joint that's being pulled by it that would cause a static error if we don't compensate for it, if we don't fix it, if we don't put an integral component in our controller. So there, that's it. That's the rationale for a PI controller inside a loop in decentralized control of servos. But now the question is, okay, I will put a PI controller there, but what's the feedback about? What quantity am I going to put in the return loop? What am I going to control over? What the control variables might be? And as it turns out, again, luckily for you, nothing new under the sun. Everything we've seen in the sensors part of this course and then in the actuators part is coming back into play here. It's your position, velocity, acceleration. And as it turns out, the more feedback loops you close, the more variables you track, and the smarter you are about all of that, the better the control will be. So let's get on with the basic schematic of position control. As we already said, schematics don't compute with podcasts, so let's tell it as a story. First of all, you will have your reference input, the trajectory given in the joint space for your particular servo. The odds are that the computer that was preparing the trajectory of the whole manipulator has done so for a particular operation space constraints given, so that the whole joint space story was computed through inverse kinematics. We aren't concerned much with that part of the story right now. So we just assume that we do have a task for our servo. It needs to follow a certain reference of its position. So a reference of position in time. So there is a trajectory for our particular servo. And so we go on to feed it in a feedback loop. That position will be compared to the actual position of the servo, and the difference of the two will be fed into the controller and from the controller to the motor itself. And as we all know, the motor itself has certain mechanical properties. It has certain time constants, has a certain inertia, and that's what's going to affect the whole control story. And of course, as we said, right in the middle of that, somewhere between the controller, the motor, there is the disturbance. We introduce the disturbance as the nonlinear effects of pretty much everything else. And so not only do we give the task of following a particular trajectory to our controller and the motor together, but also rejecting that disturbance as well as they can. So if we put a PI controller into this loop of ours, we get two parameters to tune, two parameters to play with, and see just how good the control can be. And sure enough, we can observe the two tasks of our control loop slightly decoupled. So we can talk about the task of following the reference and how good is that, and the task of rejecting disturbance and how good is that again. This is the part where I get slightly frustrated and start waving my hands because I can't show you a formula, but it's okay. It's okay. I just need you to imagine a couple of poles and zeros around. And that should be fairly easy if you remember your systems courses. So you have a system when you combine your PI controller and your motor and put them in a feedback loop. You all of a sudden have these 3 poles and 1 zero. Sure enough, this is where you ask, wait, what? And where I say, well, remember, your motor is, at least in this level of abstraction, a first order system. That dynamics of the first order delivered by courtesy of your inertia and your system's time constant. So that's one pole. Enter another pole because you're taking feedback over your position. So there's an integrator behind all that, because you remember the motor itself, its transfer function delivers velocity. To get position, you integrate it. And sure enough, your PI controller delivers you another zero and another pole. So putting that together gives you the 1 pole, 2 poles, 3 poles, and 1 zero. And with the 2 parameters you can play around with, you might get a chance to simplify that particular transfer function into dynamics you might prefer. One of almost a second order system. Now, what does almost mean in this context? Well, if the 2 poles, see, having 3 poles, one of them is going to be real, and the 2 others can be real, can be complex. In this particular case, they're going to be complex. So if you take those 2 complex poles far away from this pole, which is real, and that's 0, if you take their real parts significantly apart from these 2, and if I take you for a trip all the way there where those 2 complex poles are, and those 2 complex poles look down the real axis and stare at the real pole and the real 0, what happens? The real pole and the real 0 look really close, and sure enough, really far away, a really small dougal. And as such, they represent pretty much the same thing to our 2 poles far away. So, in the dynamical sense, they tend to cancel out, at least asymptotically, at least in a limit sense. So all of a sudden, all that matters in our system are those 2 complex poles far away. To take the poles apart, we had to use at least 1 parameter out of the 2 our controller gave us. So it was actually the time constant of the integral part. So now we're left with 1 parameter that we can tune, which is the gain of our controller, and we need to both handle that second order system we have now and also reject disturbance. To get the second order system to behave exactly how you want, which means define its natural frequency and also its damping ratio, well, that kind of sounds that it requires more than one parameter. It sure does. So changing the gain of our system is going to affect these two coupled. So we can't achieve the exact dynamics of the second order system we would really want to. But what about the disturbance rejection? Well, when you do the maths of disturbance versus the output transfer function, it turns out that the disturbance rejection is pretty much the question of this controller gain. So the bigger the controller gain is, the better the disturbance rejection is, directly proportional. And now this is the point where you say, okay, just make the gain as high as possible. But then you go back to the story of input versus output and discover that a big gain will make your second order system oscillate wildly because damping is going to be very low. You can imagine that on a root locus diagram, where as you increase the gain, the complex poles separate more and more and go up and down the imaginary axis, all the way to imaginary infinities along the asymptotes. So it seems that the position feedback is getting us somewhere, but that might not be the best solution for our control algorithm, since we will either have decent behavior of the system or a decent disturbance rejection, and we want both. So enter velocity. As it turns out, introducing another controller for velocity, be it just a P controller, will provide us with another parameter we can use to tune the whole system. And in the case of velocity feedback combined with a position feedback, it turns out that we have a movable zero now. A zero that we can adjust to be exactly at the position of the pole of our motor. So whatever the time constant of our motor is, we set the time constant of our controller to be the same, and we cancel out the two dynamics. One parameter out, two to go. And it turns out that the two remaining parameters can define the remaining second order system's dynamics perfectly. So we can achieve whatever transfer function we want in the terms of those second order systems that remain. That's very convenient. All of a sudden, that whole transfer function between the reference input and the output we want to achieve is our oyster. We can do whatever we want with it. And how many parameters does that leave us with? Well, none. So that pretty much means that while we're able to tune the transfer function there perfectly, it's the disturbance rejection that's going to be, well, who knows? It's going to be whatever the numbers say. So we can't really tune it as tuning the system, the second order remaining system of the input to output relationship is going to uniquely define the disturbance rejection ratio. And what we get, we get. We have to be content with it. And now you probably see where all of this is going. If we add an acceleration loop as well, so now we have a loop that goes over the position variable, velocity variable, and acceleration variable, and they're all nested. Now all of a sudden we have another controller, so 3 controllers in a cascade, 4 different coefficients, 4 different parameters to play with, and all of a sudden we can cancel the zero and the pole perfectly. We can tune the second order system to be whatever we want, and we can achieve the disturbance rejection to be whatever we want. And sure enough, this may sound too perfect to be true, especially if you go back to our part of the course that dealt with sensors and come back with, wait, we don't really do acceleration sensing. That is kind of true, because we usually don't have the time or the resources to measure acceleration really. So what we do is, well, take the velocity and filter it. Fundamentally, you will get a differentiated component that you can use as acceleration. So with a first order filter, you're fine. If you take as its input velocity, you will be able to extract acceleration. Now, of course, filters do introduce dynamics of their own. They do introduce lags. So if your system is supposed to be very fast, that's probably not gonna fly. And if you don't have a velocity sensor and you just want to do this whole filtering thing once again, so a second order filter that will extract acceleration from position, well, that introduces a lot more of dynamics, and that's probably not gonna fly for even slower systems. But still, it seems like a worthy cause to go for a loop of acceleration together with those of velocity and position, so that you can have your perfect tuning of everything. Now, perfection, of course, is subject to the quality of the feedback signals you receive. So, yes, given that you have good position measurements, good velocity measurements, and good acceleration measurements, you should be fine. But what if you don't? What if you don't really have enough time to collect these? And why do we insist on feedbacks? What about feed-forwards?
Cut your hair and look after your mother. Make your soup when you're sick of all the things that to a person or a bother. Take out the trash, vacuum your carpets. Listen to you when you're sad and confused. Give you directions when you're lost. They're just R-O-B-O-T-S rollers.
If we already have our position, the reference position, given in an analytic form, as computed by the all-knowing computer doing the trajectory planning, well then we can essentially get the velocity and acceleration profiles from it as well, as we have seen in the trajectory planning part of this course. So given that information, we can also feed it into our control loops. And if we do so, we're getting feed-forward, because it's not necessarily relying on the actual velocities and accelerations, but the ones computed based on the reference trajectory. And unlike the real measurements, we can have these instantaneously and use them as reference. So for faster systems in which measurements might have an issue, we should be fine with this feed-forward approach as well. And as it goes, on such a slippery slope of I can provide this as feed-forward, I can provide that as a feed forward. Well, what if I provided as feed forward the nonlinear components as well? What if I could compensate for parts of disturbance by essentially computing them? Because if we go back to the whole story of including nonlinear relationships, couplings, gravity and all that into the disturbance term in our control loops, we have to note that that sort of disturbance is pretty deterministic. We pretty much know what's inside there. It's just that we know it's nonlinear, so we couldn't include it as a transfer function of sorts. So other types of disturbance would sure enough be stochastic, would be unpredictable, would be caused by elements completely outside of our control. But the ones that are caused by our inertial components, by our gravity components, by the couplings, they're there and they can be computed. It's just the question of cost and complexity. So down the slippery slope of feed forward, there's something called computed torque feed forward control, in which you compute some of the disturbance you expect and feed it forward to compensate in the disturbance itself and to reduce the disturbance to just the terms that are significantly lower, second order, third order. Now the question of exactly how much can you feed forward in this nonlinear term is the one of time, computing time to be precise. Because the situation in the computational sense changes all the time. It changes in real time, and the control itself is performed in real time. So within one sampling interval, we need to compute everything for the next sampling interval. And do remember that for anything related to coupling and the effects of the whole manipulator, this needs to be performed by a central computer that has a vision of the entire system. So we need to send all the info to the central system. The central system has to compute the components we're going to contribute in the feed forward and return it back to all of our little loops in time for the next sampling time of the system. That pretty much constrains us, and that pretty much defines exactly how much can we compute beforehand and how much can we feed forward. So the computed torque feed forward control is a hybrid scheme. It's mostly decentralized, but there is this one little bit that's contributed by the centralized computing system. As such, it gives us a nice segue into the story of centralized control, the story of our next episode. The mathematics behind centralized control, operation space control, compliance and force control, all of which we're going to cover in the next episode, it's going to be difficult in terms of grasping all the multiple input, multiple output, and nonlinear Lyapunov control nitty-gritty details. But that makes this podcast even more important, because what I want you to understand is the rationale, the idea behind it. Because you're going to do the maths anyway. You're going to probably implement all the nonlinear methods at some point on a computer if you really need them. But it takes a bit of knowledge to know whether you need them or not, and how exactly to apply them, in which scenarios. Stay tuned for the episode 7 of They're Just Robots. And if you're a EE413 current student, do take a look at the lecture notes, videos, and other materials on the course website. And also keep your social distance, but you can stick around robots, they're fine. Robotic arm handshake is probably the safest one you can have right now, you know.
Don't be afraid, 'cause they're made of metal. They still got plenty of heart. You should think of it like it was a garden. There's fruit on the trees and you can pick it. Just don't piss them off, 'cause robots don't stick it. You need some friends and we've got lots. They're just our own